Okay. I'm actually the colloquium coordinator here too, so I usually do the intros when we have colloquium. So, hi, I'm me. I'm Mike Dekker. We're gonna do this little talk here. So I think we'll just get going. This was sort of, I've had this idea in my head a little bit for a while because a little while ago, the same year, I turned 40 and the church we go to down in Grand Rapids was turning 100. So big deal events for the 100th anniversary, and I turned 40 and we did something, but I don't entirely remember what, to tell you the truth. But we like to make a big deal out of milestones like that, nice round numbers that we run into. But what I like thinking about is how that's very much based on how we represent numbers and quantities as well. And so that's what we'll be looking at here. If you read the flyer, you may have read it and said, it looks like I said I'm 60 years old. And no, I'm not 60, but it is accurate to say I am 60 years old if you're thinking in the right numerical base. Okay? We'll get to that. All right, so milestones. So this is the picture I took when my Mazda Protege hit 200,000 miles. I was driving home from here to Grand Rapids, and I just happened to be an exit off the highway right when that happened, so I was able to pull over and take a picture. Here's the couple of the guys from How Ridiculous on YouTube who I've gotten much joy out of watching. 10 million subscribers, so of course they have to make a big special video for, anyway, 10 million subscribers. They got their little diamond play button.
Do one for 20 soon.
Maybe, oh yeah, really. This was not that long ago, yeah, 19.7. They might get there soon. Okay. Oh yeah, this was, I think, August of 21. Miguel Cabrera hit his 500th home run, so of course, big deal because it was 500. I mean, a couple home runs later, he hit his 502nd, which is cool, but nobody made a big deal out of it because it was 502, not 500. And actually, the following spring, he got his 3,000th hit, and then it was another big whoop-de-doo because it was 3,000. Can you imagine if his 3,000th hit was also his 500th home run? Like the same, the people would have had an absolute cow over that. All right. We're not immune. My wife and I had our 25th anniversary a couple years ago. We threw a big party. It was in a big barn, and anyway.
Rustic Rouge.
It was yes, that's Rust. Yes, there's. Anyway, yes, that's the place. We had square dancing. We had Mission barbecue. It was delicious and it was fun. All right. So yes, these things that end in 0, 25, we like to make a big deal out of as well, but especially the ones that end in 0. We like to make a big deal out of. So I just pulled these off the internet. Here's Bella and James's 50th anniversary invitation. Lordy, Lordy, look who's 40 is one of the dorkiest phrases I can imagine for celebrating a birthday. But people do that kind of stuff. But Bella and James probably didn't send out invitations to a big party on their 49th anniversary. But 50 is just that much more special? Okay, fine. All right, so along those lines, yes. Today is my 60th birthday. But notice I'm not saying 60 again. So, with an asterisk, and we'll get to it. I was quite deliberate when I was writing up the little abstract on the flyer to, in terms of how I represented things as numbers or what I stated in terms of words, to try and be a little more clear about what I was saying, even though it was pretty cryptic in the flyer. All right. Oh, you're good. So, now some birthdays, when we run into them, are a big deal, because sort of as society, we put some significance on them. So yeah, when you turn 13, you're a teenager. But now if you think about that, what if we didn't call 12 12? What if we called it 2-teen or something instead? Then everybody would be a teenager when they turn 12, and all these parents would be like, oh, I have a teenager now when they're 12. But no, they don't say that until they're 13, just because of the teen at the end of the word. Maybe we call 11 1-teen or something. I don't know. Get your license at 16, get to vote at 18, go have some beer at 21 legally. But I think some other birthdays are cool too. So these ages in particular, I turned 32 once upon a time. I thought it was cool to be a power of 2. I mean, at some point you're 1, and then your age doubles to 2, and then you turn 4, and you've doubled your lifespan again, and it doubled and doubled and doubled, and well, someday 64 will roll around, hopefully, and I'll have doubled my lifespan again since that time I was 32. You know what those numbers are? Squares. I mean, not... I feel bad saying not super special, but they're squares. I mean, you're a square. So 49 is cool, 81 is cool, 25 is cool. I didn't realize until later that I could have put 64 on that list as well, and 64, not even on purpose, sort of keeps showing up in this talk. Yep. What are those numbers? Primes. All right, so I like to say you're in the prime of your life when you're one of those ages, and that comes and goes throughout time. All right, but like I said, what this gets down to is how we actually represent numbers. So up here we have, this is clearly 4 little squares, and nothing about how the words we use, the numbers we use, whatever we've determined, changes the fact that that's how many squares there are. We say 4 in English. That's how many there are. And the triangles, there's actually 11 of them in that little group. Now in English and most places around the world, we use Arabic numerals. So we have this symbol that we call 4, and that's the symbol we use for anything, 4 items. 11, we actually use a pair of 1s. We don't have a single symbol that means 11. We have a pair of 1s, the way we write numbers. So that's how we represent it. Other numerals, Roman numerals, everybody's pretty familiar with, and we use them here and there and whatnot, but that's how you represent the quantity 4 with Roman numerals, or the quantity 11 with Roman numerals. I'm no Mandarin expert by any means, but a little research tells me those are the characters, the numerals. This is 4. This is how 11 is represented in Mandarin. Same quantity, same exact size of a group, just represented differently, certainly pronounced differently in different languages, but all the same size group. One more here. This is a pretty ancient one, slightly famous if you start exploring numerals and whatnot, the Babylonian system, and we'll look at it a little more closely later. But this is the numeral used for 4. This is the numeral that's used for 11. It's kind of a funky system, and yeah, we'll see it briefly. Yeah, if you go exploring these things, all these different languages and cultures and whatnot, they all have some representation for these different size groups. And there's just an unending list of different numerals, that is, the symbols used to represent these quantities, as opposed to just the number, the quantity 4, or the quantity 11. All right, stole this guy off the internet, and you've probably seen one of these guys before, and they are up in elementary school classrooms all over the place. But the basic breakdown of the decimal system, the decimal places and their values that we use. All right, so you probably remember, we've got the ones place. There's all the fractional places, and we're really not going to deal with that at all in this talk, just the nice whole number places. We got the ones place, and then we got the tens place, and the hundreds, and so on and so on. So when we write a number, we say that number, 20,387. What we mean, what listing those numerals in that order means, is just how many of these different size groups we have in this quantity. So in particular, this means we've got a couple groups of 10,000, no groups of 1,000, 300s and 6 tens, and then 7 little singles. And those all together make this quantity that gets this label. Now, the one thing you may very well be aware of too in the decimal system is that, yeah, we call them the tens place, the hundreds place, and the thousands place. But all of those groups are just different powers of 10. We get 100 because we have 10 groups of 10 and we bundle them all together into one group called 100. And then when we got 10 hundreds, we bundle them all together into one group of 1,000 and so on. So we're always bundling and grouping in tens in the decimal system. All right, and all those different sizes can be represented as different powers of 10. So, if we wanted to represent some things in different systems, we could leave 10 behind and use different size groups to do all our grouping and bundling. All right, so this one we'll look at a bit. This is the octal system, and this is in the name of the talk as well. Rather than grouping everything in groups of 10, what if we group them in bundles of 8 instead? So a number that's written in the octal system, you see a bunch of digits listed there, is telling you how many groups of 8 to the 0, so how many singles there are, how many groups of 8 there are, how many groups of 8 squared and 8 cubed and 8 to the 4th power there are in some quantity. We'll do some examples in a sec. So yeah, like I said, we're bundling in groups of 8 instead of 10. All right, so the number 123 means one group of 100, two groups of 10, and 3 singles. And we're going to look at that guy in a bunch of other systems for representing that quantity. All right, so in the octal system, one way to figure out how to represent a number in a different system, well, we're talking groups of 8, so we can just look at that and say, okay, how many, if we had 123 objects sitting in front of us, how many different bundles of 8 objects could we make? And you do a little math in your head and you figure out, okay, 123, we could do 15 groups of 8 and there'd be 3 leftovers, basically. All right, so we could think of 123, 3 singles and 15 groups of 8. But 15 is more than 8. Of all those little groups of 8, we could take 8 groups of 8 and bundle those all together and basically get another digit in our number. So those 15 groups of 8, I'm going to take, 15 groups of 8, I'm going to take 8 of those. There will be 7 of them left over. So now we have one group of 8 squared, 7 groups of just 8, and then these 3 singles laying around. So the number we know as 123 can be represented in a base 8, the octal system, instead, with those 3 digits, 173. Now, throughout the rest of the talk here, I'm going to be showing a lot of different numbers in different systems, and when it's in some base that we don't usually use, I'm going to put the little subscript right here. So this is base 8. All right. If there's not a little base there, I basically mean our good old decimal system number instead. So these are the things I thought about as putting this together. Should I say this and spelled out in letters as 15, or am I okay to put 15 right there as 15, or anyway? Little details that I considered while putting this all together. So, 123 is 173 base 8. All right. Now, when we pronounce words in English in our lovely decimal system, our base 10 system, we have lots of different words we use. We, of course, have names for all the digits, like 0 through 9 and whatnot. But we've even invented new words that kind of shorten up different size groups. So we don't say 7 tens, or we don't say 1 10 7 for 17. We just say 17. Somebody created that word once upon a time. And a lot of languages do that sort of thing, especially for some of these smaller size numbers. But we don't say 5 tens. We say 50, just because that's the word we coined for a group of size 50. The word 100 even is 10 groups of 10. Somebody decided, whenever, when we've got 10 groups of 10 together, let's call that something, and the word 100 is what got chosen. And 1,000 means 10 groups of 100 in addition. And so those are the words we use when we say numbers as well. When we say 123, that means one group of 100, 20 is our word for two groups of 10, and then we got three singles. All right, but this octal system representation that we just came up with, you should not say it's 173 in base 8, because those digits are not representing one group of 100 and 7 groups of 10. That's not at all what it's representing. So the kind of not great awkward solution for saying that number base 8 is to literally just say what I said earlier, 173 base 8. It doesn't feel great, but we don't use groups of 8 as much, so we don't have all these different words for, well, 8 groups of 8. We know that is 64 in our decimal system, but we don't have a word that's other than 64 for a group of 64 items. We just don't. Now, if you wanted to go the other way, if you had a number that was in an represented in an octal system, so this is not 31,675. This is 3 groups of 8 to the 4th, which we don't really have a name for other than 8 to the 4th, and 1 group of 8 cubed, and 6 groups of 8 squared, and so on. And if you want to turn that into its decimal representation that we're so used to, you really just got to do the math here. And we're very accustomed to doing math in the decimal system. That's how you grew up and learned to do arithmetic. It was all in the decimal system. And so we do our powers of 8, we multiply, we add everything together, and that's what you end up with. So the number 31675, base 8, is the same quantity that we call 13,245 in our good old base 10. All right, it's more interesting to go from the decimal we know to other systems instead. All right, but before you start messing around with other systems, so we did a little bit, grouping things in groups of 8, you need to talk about the digits that we use. Now, good old decimal system. Oh, number 1, backing up a smidge. Yeah, when you're in base 8, when you're grouping things in 8s, you don't even really need the digit that we know as 8, because every time you put 8 things together into one bundle, you've made this number, 1 group of 8 and 0 singles. So you don't need the digit 8. It's kind of convenient that we already have a symbol for a group of 8. I can use it as a little subscript here and whatnot. But in base 8, you don't actually use the numeral 8. And in general, if you want to be in base n, you need that many different digits. All right, so decimal system, base 10, 0 through 9, we know those guys very well. Binary is one that people are relatively well aware of. And in that case, the base is 2. So every time you get 2 things together, or two of the same item, you group them together, and you represent that with like a new digit in your number. And in that case, base 2, you only need 2 digits. It's a 0 and a 1, and that's it. Base 5, kind of just a random choice on my part, but if you were grouping things in 5s and representing numbers that way, you'd only need 5 digits, and we would basically use 0 through 4. And like I said, base 8 would be 0 through 7, and you don't need any more than that. But you can go to bases that are bigger than 10 too, and that's where things start to feel a little extra weird, because now if you're using base 12, it means you're representing numbers, but you're bundling things in groups of 12 to make new digit places, basically. Well, then what you need are 12 digits, 12 numerals for the sizes that go from 0 up to 11, basically. Now, of course, we've got 0 through 9 from base 10, so we can use those. But then we need a single symbol to represent 10 items and a single symbol to represent 11 items. And there's not a universal convention for how to do that. There is some conventions out there in terms of how to represent those guys, because we don't want to say 1, 0 for 10. In fact, when you're thinking about 10 for this talk, it's almost better to think about the word TEN as a size of a group, as some sort of quantity. Try not to think of 1, 0, because that representation only applies in the decimal system, and we're trying to work in all sorts of different systems here. All right, so the one that I like that gets used in some places are these. So for 10, we use an X, which meshes very nicely with the Roman numerals that we're more or less familiar with. And then just use an E to represent the size of a group with 11 objects in it. E for 11, basically. Some people who like to represent things in base 12 use kind of like a backwards 3 instead of an E, so it looks similar, or an upside down 2 in that spot, and that was a little weird to me. But so the thing is, you want to look at those and say X and E, and you could call them that, but they are literally just representing the same size group that we call 10. So you could see that X and just say 10 every time you run into it. You don't have to say X, and you don't have to say E for 11. You could literally just say 11. That's how many things we're talking about. All right, one more, which is hexadecimal, which has applications in computing and programming, and this base 16 system actually gets used in different scenarios. So you need 16 digits then. So we can use our 0 through 9, but then we got to go all the way up to a group of size 15 before we bundle things together in a group of 16. And the convention there is just to use A through F, and that's it. If you've ever messed around in some computer program and you're picking colors for backgrounds or font type, right? Something like that. Sometimes you can manually change colors by putting in a little code for the color, and it often has 6 digits, but it often involves the letters A through F, and that's the hexadecimal code for a particular color. I think all zeros is black, but all F's is like pure white or something like that. And that's the two extremes from basically 0 up to the highest number you can express with 6 hexadecimal digits instead. Anyway. All right, so we're going to take 123 and we're going to convert it to some other systems. We did that with Octal already with base 8, but putting something in binary, rather than trying to think, okay, first, how many groups of 2 can I make out of 123? What makes more sense is to think, well, these are all the different places for the digits. So in binary, we have a 1's place and basically a 2's place and a 4's place, an 8's place, really 2 cubed place, and so on. Go as far as you can with the biggest group that will fit in your quantity. So we've got to do all this arithmetic in base 10 because that's just how we work. That's how we function and how we learn to manage numbers. But 128 is too big, so we can make a group of 64 out of 123. So I'm going to take off my one group of 64, which leaves 59. Okay. I can make a group of 32 out of that, so I'll bundle those guys and take them out. And with 27, I can make a group of 16, so I'm going to do that. I can make a group of 8 from the 11 remaining. Now there's only 3 left, and I can't make a group of 4. So I will have no groups of 4 in my representation, but I can do a group of 2, and from the 1 left, we'll have one little group of 1. And so if you look at what we made, 123, the decimal number, can be broken up into one group of 64 and one group of 32, and so on and so on and so on and so on, so that we get... There's the binary version of 123. 111111 base 2 in binary. So in binary, there's only 2 digits to manage, the 0 and the 1, but your numbers can get pretty long because it takes a lot of digits to make decent-sized numbers. All right, doing a similar thing in base 5. There's our powers of 5, so what size the groups are in. And 125 is just too big, so how many groups of 25? Well, we can get 4 groups of 25 out of 123. And out of the remaining 23, we can get 4 groups of 5, and then there's 3 singles left over. So in base 5, 123, that quantity is 4 groups of 25, and then 4 groups of 5, and 3 singles, and that's how many there are. All right. So base 12, well, the sizes of the places in base 12 get pretty big pretty fast. So we can't even go to this 3rd digits place in base 12. We got to only count groups of 12. clearly in 123 we can make 10 groups of 12, but we don't represent that with a 1, 0 like we do in the decimal system. Out of 123 we get X, which is 10 groups of 12, and 3 little singles left over, and that's it. So the way I decided 10 and 11 would be represented in base 12, 123 is X3, or 10 12s and 3 singles in base 12. And what even feels weird is that I'm representing the base of the system using a decimal system number with my base 12 digits, and that, anyway, drives me slightly crazy. We'll fix that pretty soon. All right, hexadecimal ends up going like this. You can make 7 groups of 16. When you've got 123, there's 11 left over. But that's the letter B in hexadecimal. So 1, 2, 3 is 7B when we're in hexadecimal. That's it. All right, here's those Babylonian guys again, which is kind of a strange system. When you initially start looking at what they're doing with their symbols, it kind of looks base 10. Like, we've got different symbols for up to 9 items, and then when we get to 10 items, it's sort of bundled into a different symbol. So there's 10. And as you go through, yep, here's 2 10s, and here's 3 10s, and 4 10s, and 5 10s, and whatnot. The thing is, in this system, when you get to 59, and this, you can think of this symbol as its own little symbol. You can kind of see how they made the symbol. It kind of represents 5 10s and 9 singles, but they don't represent 60 with 6 of these guys. They roll over to a new digits place. So it's almost like, I mean, not almost, it really is like, there's a first slot, a first digits place in this system, and there's 60 different, well, technically 59. They don't have a symbol for 0, which is a whole other issue. They have 60 different symbols up through 59, and then when you've got actually 60 things, you bundle them all together and you move to the next place. And so this is essentially a base 60 system, which is sort of bonkers when you think about it. And it almost feels like there's a base 10 hidden inside the base 60. But there's a name for this. This is the sexagesimal system. Base 60, which feels very weird, but on the other hand, we take 60 things and bundle them all together and call them something else all the time. Namely, 60 seconds we call a minute, and 60 minutes we call an hour. I mean, you know, when you stop and think about it, it's so bizarre that we go up to 59 and then you add 1 and now you've got 00 and you go and like, what are we, anyway. Okay, that's strange. I had a Facebook friend a few years ago mention when he turned legitimately 60 years old, he was now 10 in the sexagesimal system. He finally went to a second digit because he got up to 60. All right, so you could ask the question. Yeah.
Do you know the symbol for this?
Yeah, I was waiting for the symbol.
Oh no, it would be one of these in the next spot. So 1 group of 60. So this is your symbol for 1, just like so you have.
But there's no 0, so there's.
That's.
So is it just moved over?
Yeah, it's essentially there's actually issues with that because sometimes. Yeah, they would separate digits just with space, and yeah. So
the
anyway,
space bars, they're 0.
Practically, yes, right. Yep.
Okay.
Yep.
Do they have computers, Aaron?
I don't know. I mean, they may.
Okay, so why did we choose base 10? I mean, what's the most likely reason? We chose to live base 10, and yeah, that's these guys right here. And if we only had 4 fingers, there's probably a good chance we would not be living base 10.
Have you read the book Hail Mary?
Oh, no.
Project Hail Mary.
Okay, yeah.
Have you read the book Project Hail Mary?
That's
That's an amazing book. Everyone should read it.
Okay. That's the guy who wrote The Martian, right?
And the alien he meets, I'm pretty sure they were in base 4.
Okay.
Because they had 4 fingers. Yeah.
Aliens Among Us?
Yes. Yes.
This is so common. There is something about animating characters where putting all 5 fingers like feels too busy or something. Homer's got 4 fingers.
4 fingers.
Calvin and Hobbes both have 4 fingers. I mean, Hobbes is a tiger, but still, he's got 4 fingers. SpongeBob has 4 fingers. Mickey Mouse has 4 fingers. Bugs Bunny has 4 fingers. I was just browsing through all these. The Disney princesses have 5, for the most part. A little hard to tell in some of the pictures, but they're supposed to be real, right? And not characters. So anyway. Now, the nice thing about 8 is that you could cut it in half a couple times and you don't have to go into like fractions. Base 10 is kind of weird. You can cut it in half, but that's it. I mean, you can divide it by 5, but that's kind of a strange number to divide things into. Or you could think of 8 as, well, let's double 3 times and we can get up to the basic size of our unit. So we do live octally in some ways. We take lots of units and we don't chop them into 10 equal pieces. We chop them into halves and quarters and eighths and all that kind of stuff. Inches works that way. When we measure in gallons, we don't do tenths of a gallon. We do quarts and pints and all that sort of thing. 128 ounces. Yeah, that's what it is.
Do they do that in other countries? Because I don't know if they do.
No.
Well, if you're in
They're on the
metric,
metric
you're
system.
measuring
Right,
in
so,
liters.
so we don't. But they
Oh, exactly.
That's
I mean,
what I was wondering. It's an
the United
English-
States system of
Yeah.
measurements is a whole separate colloquium. I mean, you go to Lowe's, you can find things that are 10 feet long and 5 feet long, but mostly it's like 8-foot 2x4s, or sheets of plywood are 4x8s. They're not 5x10 for the most part. You find them like this. I just sort of real quickly, some of these things you're very well aware of, and so I don't want to dwell on them a whole time. You know, a number is divisible by 2 if the decimal number ends in one of those numbers, 0 through 8. Divisible by 4 if the last 2 digits are divisible by 4. Now, the ones I've been surprised about sometimes that students have never heard of, like somehow you made it to college and nobody ever said this to you. How do you tell if a number is divisible by 3? Yeah, add up the digits. And if the sum of the digits is divisible by 3, then your number is divisible by 3. All right, 6, well, you just combine the 2 for 2 and 3, but 9 works just like 3 does. Add up the digits. If it's a multiple of 9, your original number is a multiple of 9. So here's just a quick example. There's a whopping huge number. Is that divisible by 3? Well, if we add them all up, we get 48. And then, well, maybe you forgot whether 48 is divisible by 3. Well, you could actually take 4 and 8 and just add them up and see, is that, I mean, maybe you forgot that 12 is a multiple of 3, and you could literally add those two up. And you can just keep doing it until you get to 3, 6, or 9, or not 3, 6, or 9, and yeah, this whopping number is divisible by 3. But notice we didn't get a multiple of 9, so it's not divisible by 9. Anyway, there's Math 420, which is abstract algebra, you can prove that. It's modular arithmetic, works out quite nicely. In the octal system, we have some similar things, but now we're bundling in groups of 8. So the digits represent groups of 8, not 10. So we get some similar stuff. I mean, 8 is our basic unit. If it's divisible by 8, that means when you divide by 8, there's no little single leftovers. So if it ends in a 0, it's divisible by 8. And we don't have any sort of trick in the decimal system for 7. There just isn't one. But in the octal system, is this number divisible by 7? It's just like 3 and 9 in the decimal system. And it has to do with the fact that 7 is 1 less than 8. It works in the decimal system because 9 is 1 less than 10. 9 is a multiple of 3, basically. So here's a number. This is not 1,234,000. This is a base 8 number, so it's 1, 2, 3, 4, 5, 6, 7, base 8. Is that divisible by 7? Well, if you add up the digits, in decimal form, you get 28. And actually, you could look at that and say, yeah, that's divisible by 7. And so the answer is going to be yes. In base 8, 28 is 3, 4, actually. And if you were just working purely base 8, 3, 4, is that divisible by 7? Well, 3 plus 4 equals 7, so yeah, sure enough. That number, I don't know what it is as a decimal, I didn't bother converting it, but that quantity is divisible by 7. So if we lived base 8 and we represented all of our numbers base 8, Well, when you turn 20, that's when you get your driver's license instead. I mean, it's a round, quote unquote, round number, and you get your driver's license. Isn't that like super special?
48.
Yeah. When you turn 48, well, that's 6 groups of 8, so that would be represented 6, 0, and if you hadn't put that together yet, that's how old
why
I
you don't
am
look 60.
today. Yes, I'm not 60, I am 60, base 8. All right? But in base 10, nobody makes a huge deal out of 48, right? Okay, why? Because we have 10 fingers and 48 is not a multiple of 10, and therefore just let the day go by. Okay, fine. Or have a colloquium and have cookies and lemonade and stuff because I'm 60. All right. This would be a real big one because 64 is one group of 8 squared, and so you would go triple digits on that birthday. I mean, it's pretty rare for people to get up to 100 triple digits, but there's at least a few people in this room that have a triple digit octal age. So maybe actually, however old you are, think about it a sec. How many groups of 8 fit in your age, and how many are left over? So what's your age octally? If you just think about it. I'm 60, as you've heard. All you 19-year-olds are 2, 3. 2 groups of 8. 3 singles. If you're 20, you're 2, 4. If you're 40, you're 5, 0. So that's like doubles up in both systems. All right. And yeah, if you're decimal 64 or older, you got a 3-digit octal age going. Year 2000 was a big deal, but year 2000 was a long time ago in base 8. In fact, 3000 was a long time ago, but 4000 is coming. So we had the whole, Y2K thing, which is probably too far away for some of you to remember, at least. But I certainly remember people worrying that, all our computers were going to shut down and society was going to collapse. It didn't. But maybe we'd be getting concerned about the year 4000 instead, coming up in 25 years. This is the one I like thinking about. What if instead of 12 digits around your clock, you just did 0 through 7 and your hour hand went around 3 times each day? So you wouldn't have AM and PM, you'd have, I don't know.
Try something.
Some 3 different sections to the day instead.
Be FM in there for sure.
All right. Oh, yeah, but we do have decimal 60 minutes in an hour, which is 7/4 base 8, like not a round number of minutes when we're base 8, so that would,
You just changed.
I think we'd have to change some fundamental definitions that we use of how long a second is, but then we could have like 64 seconds or something instead. A nice round 100 seconds, and that'd be beautiful. Okay, so maybe instead, base 8 was fine. What if we lived base 12 instead? All right. First off, there's a name for that. It's called the duodecimal system. That is the name for base 12. Kind of a weird name. We have 12 digits that we talked about earlier already. And what I want to make this better a little bit, well, like base 8, we have the symbol 8. That means a group of 8. Well, we don't have a symbol for 12 things. We have the decimal number 1, 2, but I don't want to use the decimal representation when I'm working base 12. And we don't really need a digit for 12, but I just want a symbol that represents 12. So the choice I'm making is D. And there's a good reason on the next slide for why I'm choosing D. So the decimal number that we know is 12 is going to be represented by a D. And in base 12, base D, that's one group of 12 and 0 singles. So it's a 1, 0 in base 12. Don't think 10. Try not to think 10. It's 1, 0. Now the thing is, we use groups of 12 all the time. What do you call a group of 12? A dozen. That's why I chose D. We even have a name for a dozen groups of a dozen. Don't use it a ton.
Fireworks.
What?
Fireworks.
Yeah? Oh, yeah.
You buy bottle rockets.
Oh, okay.
Yeah.
What's the word, though? A gross, yeah. A gross is 144 items, 12, a dozen dozens. So if you were naming the digit places base 12, you'd have your ones place, like you always do. But then the first slot would be the dozens place, and the next slot, a dozen dozens, 12 squared, would be the grosses place. So 279, not 279, 279 base 12, you could say 2 gross, 7 dozen 5. Which sounds totally weird and bizarre, right? But you're saying 2 groups of a size a gross, 7 groups of the size a dozen, and 5 units. Which is no different than us really saying 371. 300s. Now 70 is our special name for 7 groups of 10, and then a little single guy at the end. And this guy, so EX4 base 12, base D, well, still, E is just 11. We have a word for a group of size 11. So 11 gross and 10 dozen and 4. And maybe if we lived base 12, we'd come up with words like 60, 70, 80 for 10 dozen. I don't know. We'd fuse them together and have some word for it. Call it 10 does or something. I don't know. You know, very well we could. So the slightly cheeky name that gets used for base 12 is the dozenal system. Rather than decimal, it's dozenal. And there are actually dozenal societies, and there's an American society, American dozenal society out there you can join. Now the nice thing about 12 is how well you can divide it into different size pieces. You can divide it evenly by 2 and 3 and 4 and 6. That's way better than just 2 and 5 for the decimal system. And like I said, we work dozenally quite frequently already. I could have put fireworks on the list, apparently. Dozen eggs, dozen donuts. I mean, why do they sell a dozen donuts? Doesn't a box that's like 3 by 4 make more sense than a box that's like 2 by 5 or something? Like, that's weird. So yeah, dozens all the time. Even cans of pop come in 12 packs or 24 packs or 6 packs, which are just half dozens. 12 inches in a foot. Which does mean we could say things a little differently. If you're 5'11", I mean, you can still say, I'm 5'11", or write 5-E though. You'd still say it verbally the same, but symbolically it'd look a little different. 5E, 5'11". We got 12 months in a year, for Pete's sake. And one thing I like about this that would make that a little cooler, we number the months and we use numerical dates all the time. But we have to go to 2 digits for the month all the time because there's 12 of them and not just 10. So what if we numbered them instead? January, so we 1 and so on. But now October's not, well, it is 10, but it's got the symbol X. And November is the symbol E. December can be the D. And you can use 1 digit for your birthday month all the time instead of having to, I mean, 3/4 of us have to do 0, 7, 0, 3, whatever. Just 1 digit. 1, 2, all the way out to X, E, D, like so. So that would be my birthday. E14D, 1187D. Which you can figure out in decimal if you realize I'm 48 today and do the math. Anyway. All right, each day, 24, 2 nice round dozen hours in a day. And our clock goes around 2 times. Now, like with the octal system, it might make sense to change our definition of seconds and minutes a little bit so we can bundle them a little more nicely. Because 60 base 12 is 50, which isn't bad. But 6072 is so nice. That's exactly a half dozen dozens. It's a little more round than actually having 60. And in fact, using all those digits we talked about, you could use 0 for 12 o'clock or D for 12 o'clock. You can get a clock that looks like this. A nice single digit all the way around. There's the X, and here's sort of the upside down 3, backwards 3 kind of thing. You can get that on Amazon right now. It's on my Christmas list. One thing to notice is that they are taking every hour or every there's 12, there's a dozen seconds in here. So they actually have 144 seconds in a minute, or 144 minutes in an hour. And I like this. I mean, 72 is just closer to what we already do. So 144 would seem like a real explosion, or a real.
Really be ticking quickly.
Yeah. Oh, with that too. Yeah. You can get nice little animated base 12 clocks online, and it feels like it goes around pretty fast. All right. So I don't know. Maybe base 12 is better than base 8. We've got so many things that have come in groups of 12 already, so I guess we should be living, maybe not base 8, but we'll go base 12. So, I mean, it was great that I was 6048 today. That's fine. I mean, it was a fun idea and whatnot. So, well, but if we go base 12, then what am I? 40! Sorry, I said it wrong. 40. So, okay, I'm not 60 base 8. Forget that. Oh, I'm still a nice big round special birthday today in base 12. So, yay, there you go. So maybe that's what the title should have looked like
Aw.
instead. The end.